Because the universe contains matter, it should also contain antimatter. However, based on observations, no permanent antimatter exists. This is a huge mystery because, according to particle physics, when the Big Bang produced all the matter found in the universe, it should have produced an equal amount of antimatter. So, since there is an abundance of matter, there should also be an abundance of antimatter. Assuming it does exist somewhere, the big question is, where is the antimatter? What if the missing antimatter is actually all around us, just hiding in plain sight? Here, I present a case that shows why the missing antimatter is probably integrated within most of the particles we call matter, but because of a couple of misinterpreted past experiments, we were unable to make the discoveries that would ultimately reveal its whereabouts. In 1961, theoretical physicist Murray Gell-Mann devised a scheme to organize baryons and mesons he called the Eightfold Way. In 1963, he showed that using charged particles he called quarks, he could model baryons like the proton using 3 quarks, and mesons like the pion using a quark and an antiquark. While the quarks and the Eightfold Way did model the particles well, at the time, everyone knew the proton was fundamental and not made of smaller particles. And, since the quarks also had to have fractional 1/3 charges, no one considered quarks to be real particles. They were seen as just a mathematical device used to flesh out the Eightfold Way. Then, in the late 1960s, a series of experiments called deep inelastic scattering were conducted at the Stanford Linear Accelerator Center, or SLAC. These experiments fired high-speed electrons into proton targets, similar to experiments where Ernest Rutherford fired alpha particles into gold foil. The SLAC experiments were designed to show that the interior of the proton was homogeneous, making the proton a fundamental particle. However, instead of the electrons just passing through the protons as expected, they scattered at angles indicating they were bouncing off particles inside the protons. This discovery made Gell-Mann's quarks begin to seem real. Structure functions, called F2, were calculated from scattering data and plotted as a function of the proton's momentum fraction x they corresponded to. Richard Feynman devised a way, using the F2 structure function, to determine the number of particles inside the proton he called parton theory. According to parton theory, the F2 values should peak at the x the particles inside the proton carry and go to 0 as x approaches 0 and 1. This meant that for a proton made of 3 particles, the SLAC F2 needed to peak at about x equals 1/3. When the analysis was done, the SLAC proton F2 curve did not peak at x equals 1/3. It appeared to stay constant as x approached 0 from about x equals 1/5 down to about x equals 1/16. No data was produced below x equals 1/16, but the F2 was assumed to stay constant down to x equals 0. This seemed to indicate that the proton was not made of 3 particles as Gell-Mann had proposed. However, it was determined that, if in addition to the 3 quarks, the proton contained a distribution of virtual quark-antiquark pairs, later called C-quarks, the F2 would remain constant as x approached 0 as observed. From this, it was ultimately declared that the proton is made of Gell-Mann's 3 quarks, called valence quarks, plus a distribution of quark-antiquark pairs called the C-quarks. Subsequent analysis found that, to balance the momentum distribution of the quarks, uncharged force-carrying particles called gluons were needed in the proton model. The gluons were thought to bind the quarks together within the proton. So, by the early 1970s, the proton became Gell-Mann's three quarks and a distribution of quark-antiquark pairs, all held together by a collection of chargeless gluons. Deep inelastic scattering done in the early 1990s at the Hadron Electron Ring Accelerator, or HERA, used much higher electron-proton collision energies than SLAC. Covering X values down to 0.000178, about 1 over 5,600, HERA showed the proton F2 was not constant as X approached 0, as SLAC indicated, but rose sharply. This was thought to be because of the gluons in the proton the lower energy SLAC experiment could not see, and seen as a validation of the gluons in the proton. By the mid-1990s, this proton model had become, and still is, the standard model. However, in the year 2000, the Thomas Jefferson National Accelerator Facility, or JLAB, also did a set of electron-proton deep inelastic scattering experiments. The JLAB experiments were done at collision energies comparable to those in the SLAC experiments and covered momentum fractions down to X equals 0.009 or 1 over 111. These experiments indicated that, unlike the results of the high-energy HERA experiments that showed the F2 rising as X approached 0, at energies comparable to those of the SLAC experiments, the F2 actually approaches 0 as X approaches 0. As a result, when the SLAC and the JLAB F2 values are plotted together, the F2 curve peaks at about X equals 0.11 or 1/9. According to parton theory, this means that the proton appears to have 9 particles within it. The proton is made of 9 particles. Although the JLAB data is available, it apparently has never been used to reevaluate the proton model. If the proton is made of 9 particles, given its mass, those particles are likely either muons or pions. While analyses done at SLAC in the 1960s concluded that the component particles of the proton were spin 1/2 particles, which favors the muon, the analyses did not support the spin 1/2 conclusion for the range of X values the component particles fall into, suggesting the particles are probably spin 0 particles. Spin 0 components favor the pion, which seems more likely since, many times when a proton collides with other particles, several pions appear in the debris. So, although it is commonly believed that the proton is made of 3 quarks, maybe it is actually made of 9 pions, 5 positive pions and 4 negative pions. Of course, if pions are made of 2 quarks, as Gell-Mann proposed, then a proton made of 9 pions contains 18 quarks. Thus, the proton is still made of quarks. But, are pions made of quarks? The HERA data seems to suggest otherwise. In the HERA experiments, the high-energy probing electrons have a much shorter wavelength than those of the low-energy SLAC and JLAB experiments. This means that the HERA electrons can see finer detail within the proton than the SLAC and JLAB electrons. They have a higher resolution. From the SLAC-JLAB F2 curve, their electrons can resolve the pions within the proton. The HERA F2 curve indicates its electrons are apparently seeing particles much smaller than the pions. Noticing the HERA F2 curve begins to diverge from the slack JLAB F2 curve at about x equals 1/9 as x approaches 0, it appears that once the HERA electrons have resolved the pions within the proton, they begin to resolve the structure within the pions. If the 1/9 proton momentum fraction the pions carry is set to a momentum fraction of 1 for the pion to represent the whole pion, and the peak proton F2 value, about 0.36, is set to 0 for the pion to make the F2 for a whole pion 0, then the HERA F2 curve is transformed into a pion F2 curve. When the curve is magnified, it shows a peak of about x equals 0.0049 or 1/204, which indicates that each pion within the proton is made of about 204 smaller particles. Since there appears to be 9 pions in the proton, this means that the proton is made of about 9 times 204 or 1,836 particles. The proton's mass is about 1,836 times the electron's mass, so it appears the particles making up the pion and the proton are about the same mass as an electron. The proton has a charge of +1. To get this charge, using only electrons, the proton is probably made of 1,837 electrons, 918 negative electrons, and 919 positive electrons. The negative electrons are just electrons, and the positive electrons are positrons, so it appears the proton is made of electrons and positrons, matter and antimatter. The antimatter particles created in the Big Bang apparently paired up with the matter particles created to form the components of the proton. But how can that be? When matter and antimatter encounter each other, the two supposedly annihilate. Once again, parton theory may provide the key to solving this puzzle. According to parton theory, F2 curves with blunt peaks, much less than 1, indicate that the particles they represent interact strongly with each other. They likely bind together like the nucleons do in the nucleus of an atom. The blunt peak of the proton F2 curve, at about 0.36, indicates the 9 pions in the proton are tightly bound together. This is supported by the fact that the pions in the proton each have a mass of about 204 electron masses, whereas the free pion is about 273 electron masses. This is a mass defect of 69 electron masses, or about 35 MeV. Having 9 pions in it gives the pions in the proton a total mass defect of about 315 MeV, which becomes the binding energy of the proton. By comparison, the alpha particle, made of 2 protons and 2 neutrons, has a binding energy strength of just 28 MeV, about 1/11 the apparent proton strength. On the other hand, parton theory says that F2 curve peaks that are sharp and near 1 indicate the particles represented by the curve do not interact strongly. They are likely configured in orbitals like the electrons of an atom and consequently never come in contact with each other. The sharp peak of the pion F2 curve at just under 1 suggests the electrons and positrons that appear to form the pions never come in contact with each other. This is why they do not annihilate each other inside the proton and did not annihilate each other when the pions that became proton components formed. So, if every proton has 919 positrons and 918 electrons in it, and every proton in existence has a matching electron, then assuming neutrons, being neutral, are made of the same number of electrons as positrons, based on neutron decay, likely 920 each, there is an equal number of electrons and positrons, matter and antimatter, in the universe. While this may sound far-fetched, given what we are taught, recall that, during beta decay, both electrons and positrons appear to exit from the nucleus. Historically, the idea of these particles actually emerging from within the nucleus has been dismissed, mainly due to uncertainty principle constraints, but perhaps those restrictions are misplaced for the electrons and the positrons that appear to reside in protons and neutrons. Notice that where it takes only 1,836 free electron masses to make the proton mass, it takes 918 electrons and 919 positrons, a total of 1,837 of the particles inside the proton, to make the proton charge. This suggests that the electrons and the positrons found inside the proton, call them beta electrons and beta positrons, are slightly less massive than the electrons outside the proton, the free electrons. Also note that during beta decay, when an electron exits the nucleus, it is accompanied by an electron antineutrino, and when a positron exits the nucleus, an electron neutrino appears with it. Where do the neutrino and antineutrino come from? It may be that beta decay occurs because an excess of beta electrons and beta positrons in the nucleus makes it unstable, causing some beta electrons and beta positrons in the nucleus to eventually annihilate each other. Some of the resulting energy produced by the annihilation kicks either an excess beta electron or excess beta positron out of the nucleus, and simultaneously some of the energy creates an electron-neutrino-antineutrino pair. An exiting beta electron captures the neutrino to become a free electron, or on its way out, a beta positron captures the antineutrino to become a free positron. The captured neutrino and the free electron and antineutrino and the free positron make the free particles slightly more massive than the beta particles in the proton. The neutrino or antineutrino not captured during the decay accompanies the free positron or free electron respectively out of the nucleus. The pair production of the neutrinos during the decay preserves the matter-antimatter balance in the universe. If the free electron is truly a beta electron coupled with an electron neutrino, and the free positron a beta positron coupled with an electron antineutrino, then they are not truly fundamental particles. They, like the protons, have parts. It now appears that the real fundamental particles are the beta electrons and beta positrons found inside the proton. In fact, along with the electron neutrino and antineutrino, the beta electron and beta positron appear to be the four fundamental particles that make up all the stable matter in the universe. So, where is the antimatter? It appears to be meshed in with the matter to form the neutrons and protons found in the nucleus of every atom in the universe. It's all there, just hiding in plain sight. But I found it.